In this set of notes, we're going to continue looking at multiple linear regression. So once we've concluded that we have a useful multiple linear regression model, we're ready to use that model for estimation and prediction. And you're going to notice that using this model for estimation and prediction is going to be very similar to when we use the simple linear model for estimation and prediction. So again, we're using those same concepts. However, the standard deviation for the estimator y hat is rather complex, and it is written in matrix form. So if you go back to that chapter 5, or probably that module 5, that's one of the reasons that was so important, because that matrix form extends past just simple linear regression. So if we wanted to, we could use that matrix form to find the standard deviation of the estimator y hat. But for right now, we're just going to use software to find these intervals. All right, so notice here we've got two different types of intervals. We have the interval for the mean response, and if you'll remember, that is when we talk about estimation. So this is when we're trying to estimate what is happening on average. And then we have prediction of the response. And again, when we look at prediction of the response, that's when we're talking about the prediction of an individual response. And so here we have the 3 steps of how you would calculate these. And so, for example, looking at the estimation interval, to find that confidence interval for the mean response at a particular set of values, the 4 assumptions of the multiple linear regression inference need to be met in order for this to be valid. But notice, if you've already determined that the model is useful, you've actually already checked all of those assumptions. So if we were to find this interval for that confidence interval, we would find our critical value, which is still going to be a t-value, but notice the degrees of freedom are slightly different here. So before we had n-2 because we only had a single predictor. Now our critical value is found with degrees of freedom n-k+1, where k is the number of predictor variables. We would then compute the point estimate. And so we saw how to do that with simple linear regression, but that's essentially where we take our prediction equation, we plug in the values of the predictor variables that we are interested in, and then we can construct the confidence interval. And so notice the form of the confidence interval is very similar to what you've seen before. It is going to be that point estimate plus or minus the critical value times the standard error of y hat. And so you've seen many confidence intervals take this form, and so the idea is usually the same. Our statistic is at the center of the interval, and then what we're doing to account for the uncertainty is we take into account, 1, the sampling distribution of our statistic, and that's usually taken into account by the critical value, and then we also look at the standard error, which helps us account for the amount of variability. All right, very similar steps for the prediction interval. The one difference here is, notice that when we talk about the standard error, we get a little bit of extra error there in the form of s squared. And if we remember before, when we looked at simple linear regression, we saw that the prediction intervals are always wider than the estimation intervals. So that should be no surprise. So let's look at an example of this. So this is our running example for multiple linear regression. Remember that we have this professor who is studying levels of racial animus across different areas in America, in particular looking at different media markets. And so what animus is it's a value derived from this algorithm, and it is scored between 0 and 250. We have observations from 196 different media markets. And we're going to look at 4 different independent or predictor variables given here, and we've seen these before. So we're going to interpret a confidence and a prediction interval for animus for a media market with the following. So notice here we're given the values of the 4 different predictor variables. And here we have our output. And so you'll notice this R output, again, looks almost exactly the same as when we looked at the R output for the simple linear regression, and the same thing will be true of SAS output. So notice here in the first one, we have the interval as confidence. In the second one, we have prediction. So we know the first one is going to be our estimation interval or our confidence interval, and then we know that the second one is going to be our prediction interval. So let's identify both of these intervals and interpret them. So for the confidence interval, if we look here, we have the lower and the upper bound for the interval. Let's just round these to 2 decimal places for this example. All right, so there is our confidence interval. So let's interpret this one. So since it's a 95% confidence interval, we are going to say we are 95% confident. And since this is a confidence interval or an estimation, with it we are looking at mean animus score. So this is the mean animus value for a media market. And in particular, this is going to be I have messed up here. It should say mean animus value, not for a single media market. This should be for all media markets. Because if we're talking about mean, we can't have a single one. So we're 95% confidence that the mean animus value for all media markets with, and so notice this is in particular to media markets with these 4 values. So notice if we changed any of those values, we would get a difference confidence interval. And then we can say lies between, and we give the values for the confidence interval. So again, since this is a confidence interval, what we're looking at is we're looking at estimating the mean for all media markets. On the other hand, we're going to look at the prediction interval next. And so for a prediction interval, we're looking at a single media market that has these values. So for the 95 prediction interval, we say with 95% confidence, we predict for a single media market with the values given above for the 4 predictor variables. The animus value will fall between. Let me go up here and look at that interval. And so remember, here's our prediction interval. So we've got 49.7 and looks like we have 148.91. So again, the difference between these 2 types of intervals are exactly the same as when we talked about simple linear regression. Really the only difference here is that, we've got more predictor variables that we're plugging in to our prediction equation. All right, so far when we've talked about these models and we have fit them, we have looked, or we've considered each of the predictor variables to be independent. In other words, when we looked at our model, we had something that looked like this. So if we had only 2 quantitative independent predictor variables, we would have the intercept beta 1, beta 2 times each of them. So in other words, what we're saying when they're independent is they don't depend on each other. So let's look at kind of visually what this looks like. So suppose we have the model with beta not equal to 1, beta 1 equal to 2, and beta 2 equal to 1. So in other words, I'm giving you the parameter values. So we're not estimating these based on data. We're actually saying, okay, this is what the parameter values are equal to. So recall that we saw in module 6.3 that for different values of x2, we have parallel lines. And so you may want to take a minute, go back to that module 6.3, and just remind yourself of that example. So now let's consider the case where x2 changes given the value of x1. This is what we call an interaction effect. So in order to allow for this effect, we add an interaction term denoted by x1, x2 to the model. And this results in the following second order model. So notice the reason we're calling this a second order model is because it has a second order term, which in this case is the interaction term. Later on, we're going to learn there are different possibilities for second order terms. So for example, we could have like an x1 squared or an x2 squared. And so we'll learn about that in polynomial regression here in a couple weeks. All right, so suppose now we have a model. Similar to before, I'm giving you what the parameters are. So these aren't based on data. I'm actually saying these are the parameters. Alright, and so now let's look what happens to the expected value of y as we look at different values of x2. So we're going to start out with when x2 is equal to 0. So again, looking here is our model, and then here is the value of the parameters. So we are going to have beta naught is equal to 1 plus beta 1 times x1, which is going to be 2 times x1. Oh, I just realized there's a typo here. This is a beta 2, not a beta 1. I'll fix that in your all's notes. Then we're going to have minus 1 times x2, but we just said that x2 is equal to 0, plus beta 3, which is 1, times x1 times x2, which again is equal to 0. So notice this is going to be equal to 1 plus 2x1. Alright, we can do the same thing for when x2 is equal to 1 and for when x2 is equal to 2. So let's do that. So here we're still going to have 1 plus 2x1 minus 1 times 1 plus 1 times x1 times 1. And so notice here, what's going to happen is we're going to have 1 minus 1, which is 0, and then we're going to have 2x1 plus x1, which is 3x1. And if we do something similar for when x2 is equal to 2, we get minus 1 plus 4x1. So notice here, as we look at different values for x2, the slope on x1 is changing. So this is what we mean by an interaction term. So let's now look at what that plot looks like. So we see the important effect on the expected value of y. The change in x1 or the slope now depends on the value of x2. So these two variables interact. So what's happening is when we plot these lines, notice the lines are no longer parallel, they now intersect. So that's one way when we think of the difference between considering the independent variables to be independent from one another where the lines are parallel, in an interaction they are now going to cross. And again, that's because the slope on x1 or the effect of x1 now depends on what level of x2 that we have. And so this cross product x1, x2 is called the interaction term, and the following model is an interaction model with two quantitative variables. So notice here we've got two quantitative variables, x1, x2, and then we have the interaction term. And what you could show with just a little bit of algebra is if we look at beta 1 plus beta 3x2, that represents the change in xy for every 1 unit increase in x1, holding x2 fixed. And then beta 2 plus beta 3x1 represents the change in the expected value for every 1 unit increase in x2, holding x1 fixed. So notice these interpretations look very similar to the interpretation of the slope, but they're now more complex because of the addition of that interaction term. So as we add higher order terms into our regression model, what we're going to find is those nice interpretations that we had earlier on with simple linear regression, or even that model where we considered everything to be independent, those nice interpretations are going to get much more complicated. And so you really want to be aware of that, because in practice we normally include higher order terms, we include a lot of variables, and so you want to be very careful of how you're interpreting the values of the coefficients. All right, so let's continue looking at that running example that we have. And so now what we're going to do is our data set still contains observations from 196 different media markets, but we're going to look at only 2 predictor variables. We're going to look at the percentage of those with at least a bachelor's degree living in the media market, and the percentage of those who are at least 65 years old living in the media market. So do notice that we have relabeled what X1 and X2 are for this example. And we're going to consider this second order regression model. So in other words, this is that second order regression model with the interaction that we just saw right here. So it's that interaction model with 2 quantitative variables. So here's our new model that we're fitting, and here is the SAS output. Now, one thing I just want to slightly note it, and you'll see this in the lab. So we're no longer going to use the proc-reg statement. We're actually going to use what's called the proc-GLM statement. You can make the proc-reg statement do interactions in higher order terms, but it's a little more complicated, and it's really better just to switch over to the proc-GLM. Now, one thing that is new in the SAS output that you haven't seen before is this middle section right here. So when we use proc-GLM, SAS actually computes 2 different types of sum squares. There are the type 1 and the type 3. Sometimes these will be equal to one another, sometimes they will not. I'm not going to discuss these too much right now, but in general most people do go with the type 3. And the pieces of the output we're going to use, which is this piece up here and this piece down here. This piece down here, when we look at our hypothesis test, these are computed using the type 3 sum squares. Now, one of the things that I'm going to show you in R, you do have to be very careful in R. When we use the summary of our model in R, R will give you these exact same hypothesis test. It will use the type 3 sum squares. But if you do the ANOVA and get the ANOVA table, it's going to use the type 1, and we have to actually force it to do the type 3. The difference between the two deals with how they're calculated, whether or not they're calculated sequentially. And so again, we'll talk about that later on. But for right now, that's kind of getting in the weeds, and we don't really need that. But I did want to mention it in case you were wondering why this output looks slightly different than what you have seen before. All right, so looking at the piece of the output we're most concerned with, notice here, if we look at our parameter estimates, this is very similar to what you have seen before. We have our intercept, so there's going to be our beta hat naught, beta hat 1, beta hat 2, and beta hat 3, so we do have the interaction. Now, one thing to notice here is we do actually want to be careful, because how I have modeled these up here, notice that I've actually labeled X1 as those with a bachelor's degree and X2 those with at least 65 years old. So really, when I come down here, this one is the beta 2 and this one is the beta hat 1. The values won't change if you flip the order, but this is one of those things to consider if you're thinking about writing up your results. Do make sure that you're matching between the two. Alright, so the first thing we're going to do is we are going to interpret those beta estimates. So in other words, all of those beta hats. So the one thing that we really want to be careful here is that interpretation of beta hat 1 and beta hat 2 are going to be different compared to that first order model that we saw before. So previously we discussed the change in mean response, which each unit increase on X1 with X2 held fixed, or vice versa. But now that beta hat 3, that interaction term, also involves X1 and X2. So we have to be really careful here when we talk about what we mean by the interpretation of the beta estimates. So to motivate this, consider the following. We are going to compare y hat, beta hat naught, plus beta hat 1 X1, plus beta hat 2 X2, plus beta hat 3 X1 X2, and I'm going to call that expression 1. So let's see what happens when we increase x1 by 1. And notice the reason I'm doing this is before, when we've talked about the interpretation of beta hat 1, we've always talked about a 1 unit increase in x1 to see what then happens in y. So I'm going to look at y hat, and I'm going to call it y hat new. And so y hat new is going to be what happens when x1 is increased by 1. So the only thing I'm doing here is everywhere I've got an x1, I'm going to substitute an x1 plus 1. Okay. And now what I'm going to do is I'm going to multiply everything out and combine some terms. There's a 1 there. All right. So the next thing I'm going to do is notice we've got this beta hat 1 and I've got this minus beta hat 3 x2. So what I'm going to do is I'm going to subtract that from both sides. So now notice I've got y hat new minus beta hat 1 minus beta hat 3 x2. And notice this is equal to the following. Okay. And so you might be asking, well, why did we do that? Well, what I'd like you to do is look at the right-hand side of this equation compared to what we have up here. So really, the right-hand side of these equations are now the same. So what this does is it allows us to equate our left-hand side with our right-hand side here. In other words, it's going to let us see really what is the difference between y hat and y hat new when we increase x1 by 1. So notice what we have here is that y hat new is equal to y hat plus beta hat 1 plus beta hat 3 x2. Okay, so that's just from rearranging those terms just a little bit. So the important part to notice here is this piece right here. Okay. So what this tells us is the following. When x1 increases by 1, y hat increases by beta hat 1 plus beta hat 3 x2. And notice that the first order interpretation does not have this. So interpreting the beta estimates is much more complicated here. We can't talk about the interpretation of beta hat 1 like we did before, because the interpretation of what happens when x1 increases by 1 actually involves both beta hat 1 and beta hat 3 times the value of x2. So for this reason, we generally don't talk about the interpretation of the beta hat 1 and the beta hat 2, because again, it's much more complicated than it was before. So be very careful when you think about as you add in different pieces into your model, what that is doing to the interpretation of those beta hat 1s. Because you don't want to misinterpret and say, oh, well, this effect is this, when really what we're looking at is something much more complicated. All right, now what we can still do, though, is we can still look at the overall utility of the model at the 5% level. And so just like before, with any of our interpretations, we always have to make sure that those assumptions are met. And so for right now, we're just going to assume that those have been checked and they are good, because again, we're going to spend an entire week where we look at how to check all these assumptions and do full checks for a model. So we're going to check that later, but we do want to acknowledge that we know that it is important that those assumptions are met. All right, so we're going to test this at the alpha equals 0.5 level, 0.05. So let's see for the overall model utility what our hypotheses are going to look like. So when we look at the overall utility of the model, it's actually very similar to when we looked at the model without the interaction. We're still going to look at each of our parameters, and under the null, we're going to assume that they are all equal to 0. And then under the alternative, we're going to try to prove that at least one of them is non-zero. So next thing we're going to do is we're going to need to identify our test statistic, which is going to be an F, and our p-value for our overall model. And so in order to do this, we are going to want to go back and we're going to look at that SAS output. So let's go up and look at that SAS output. So this is going to be the first piece of the SAS output. This is what we're going to want to use. And so notice here, we have our test statistic and our p-value. Right, so our test statistic is 23.48, and our p-value is actually going to be something less than 0.0001. Now, one thing to notice is in a publication, whenever reporting F values or F test statistic values, it's always a good idea to include your degrees of freedom with those. So you will often see that. So let's go back up to our output. If you're going to report this for a publication, remember here are your degrees of freedom. So your numerator degrees of freedom are 3, and your denominator is 192. All right, so we've got our test statistic, we've got our p-value, so let's go ahead and conclude our hypothesis test. Notice our p-value is obviously less than our significance level, and again, in a publication, you could just report the p-value is less than. You don't necessarily have to talk about at a particular significance level. That is something that is currently changing in the way that publications are written. So here, I am going to stick with the traditional looking at the p-value less than 0.05, but again, keep in mind that this is something that is currently changing. So there is sufficient evidence at the 5% significance level to conclude that the model with the 2 predictor variables and remember what those 2 predictor variables are. We're looking at the percentage of those in the median market with at least a bachelor's degree and the percentage of those that are at least 65 years old, and the interaction is statistically useful. At predicting animus value. Alright, so this overall model utility test, whenever you're doing any kind of multiple linear regression, whether it be that first order, a second order, polynomial, it doesn't matter. This overall test of model utility, this is always the first thing that you do. Essentially, this test is just saying, is your overall model useful at all? Now, once you do this test, then you can start looking at the individual pieces of the model to see if they are useful. And so we saw this in the previous week's note set. That was one of those comments. So this overall test, this is always your first step. You do this first, and then you figure out, okay, are my pieces that I have in my model, are they useful? So the next thing we're going to do is actually test that interaction term. So we might have fit the overall model, it's useful, and so the next question is, well, do we actually need the interaction term? Because it could be possible that the interaction term is not significant, and so you could remove it and refit the model. So here, we're going to test the hypothesis test at the 5% level that the animus bachelor's slope increases as the percentage of those who are at least 65 years old living in the median market decreases. So in other words, this is saying that the two predictor variables interact negatively. So again, the very first thing for this hypothesis test would be to make sure the assumptions are met. But if you've already checked the assumptions for the overall model, then you know that those assumptions are met. So let's look at what our hypotheses are in this case. So our null hypothesis, notice that we're interested in the interaction term. So we're only interested in beta 3 for this hypothesis. And we're interested in if the variables interact negatively. So here we're actually testing to see if beta 3 is less than 0. If we were just testing to see if they interacted, then we would have not equal to 0. Positively would be greater than 0. And of course negative is less than 0. So the next thing we need to do is, again, we need to find our test statistic and we need to find the corresponding p-value. Now the test statistic in this case is going to be a t-test statistic. And again, we're going to go back to our SAS output to find these values. So let's go back up to our SAS. So now this is where we're using this second piece of the output. And so if you look here, we have our interaction term, and you'll notice here we have our t-value and our p-value. So going back to our hypothesis test, notice in this case our test statistic was equal to negative 3.93, and we had a p-value that was very small. So again, since our p-value is less than our significance level, we are going to reject the null hypothesis. So here we can say at the 5% significance level, we can conclude that the rate of change of the mean animus value of media markets with a certain percentage of bachelor degrees decreases as the percentage of those 65 plus increases. Alright, so just a couple general comments. Again, test the utility of the model using that global F-test. We do that first. If the model is useful, then you go ahead and you check the interaction to see if you need it. If the interaction is detected, the first order term should not be conducted because they're meaningless tests. In other words, the presence of the interaction implies that both of the x's are important. So you want to think of, you always test the overall model first, Then you test your higher order terms. If your higher order terms are significant, you maintain all the lower order terms. So in other words, if the interaction is significant, we automatically maintain the first order, or the main effects, the x1 and the x2 effects. So the concept of interaction is not always intuitive, and you are going to rather know a priori or beforehand whether the two independent variables interact. So the choice to include an interaction in a model should not be based on whether or not you think a priori these variables interact. We do want the data to tell us whether or not there is an interaction present. So because of this, you're always going to need to fit and test the interaction term to determine its importance. We can't just decide that beforehand. And this is one of the things that, as we start to build on the idea of model complexity, is going to become very important. If we think of, I'm going to have 10 variables that I'm going to include in my model. Well, it's not just really including those 10 variables. You really have to consider, these 10 variables might all be interacting with one another. And so you can imagine that models, as we include more variables, can get pretty unwieldy pretty fast. And so that's why, as we move on in the course, we talk about more complex models, we are going to get to the point that we talk about which variables do we include. We want to be selective and make sure we're only including variables that are actually important, because we're going to have to also consider all of these higher order terms as well. And again, as you could see just in this simple example, our interpretations, they get very much more complex, and how these things are interacting with one another can become very complex.